Hello, everybody. Yes. Okay. So, are the slides on Canvas yet? No, no. We are post the slides and also the recorded version of the session after the sessions. Maybe for some sessions we will probably release the slides before, but yeah, they're not right now. Okay. So, please say hello if you can hear me.
Hello.
Hello.
Hey,
Hi.
great. I,
Hello.
I thought I muted you, but it's fine. It
Hello.
doesn't worry. Hello, everybody. Okay, so we
Hey.
have 93 already. Let me know. Yeah, so we have more people joining the course. Great. Okay. So give me a second. Please say yes on the chat if you can see me.
Can see you.
Perfect. Great. Let me just turn my light. I have another lighting here. Great. Okay. So now the lighting is correct. Okay, great. So my name is Enrique Rosales. I will be your instructor for this course for the entire term, and I'm very excited about it. I hope you're as excited as me. Um, the setup of the online course is obviously not the ideal for everyone, so we understand that. I understand that. At least I think right now we should have 135 people, and we have roughly 98 people. Oh, we have more people waiting actually. Middle, yes. So some of you are not going to see the course synchronously, right? And I understand that could be hard. We are doing our best effort to make the class as nice as possible and as efficient as possible. Um, COVID-19 pandemic is creating a lot of mess. I understand also that maybe some of you are facing maybe stress or personal problems. I'm already lost someone from my family due to the COVID-19 problem, and yeah, so I understand that this could be hard, but again, we will try to get fun and learn a lot. Okay, so let me see. We are still 4 people waiting. Okay, wow, 103. That's nice. Okay, 2 more people waiting. Okay. I don't know. It seems that I need to click this several times. Okay, so let me just make a very quick introduction of myself. Again, my name is Enrique Rosales. I've received a couple of emails from you calling me Professor Ruiz. For some reason, the thing is, I have 2 names and 2 last names. In Mexico, that is usual. I am from Mexico. So my complete name, and also with the correct pronunciation, is Enrique Alberto Rosales Ruiz. It's super long and it has this R sound from Spanish. But Ruiz is my second last name, so I almost never use it. I don't know why in the system it shows Ruiz. So yeah, so just Enrique Rosales is fine. Enrique is perfectly fine. So if you want to call me or whatever, Enrique is perfectly fine. And I'm a PhD student here at UBC. I'm in the Imager Lab. I work with Ala Schaefer. The Imager Lab is the computer graphics area from computer science department, and it's also like divided in like subgroups. So the group of my boss is called DGP, geometry processing. So that is what the area in which I am involved. And this will be hopefully my last year, so I will probably graduate next year. And again, I'm super excited to teach this course because I have a little bit of experience before. At least at UBC, I've been TA from this course before, and but I've been teaching before coming to UBC. I have experience teaching either computer graphics or computer graphics related courses since 2003, I think. So 17 years already. I've been teach procedural modeling, computer graphics, particle simulation. Yeah, many topics. So yeah. I will stop talking about me right now because that is not obviously the thing on on the course, and I will jump into the presentation. Okay. So besides me, good. So besides me, we have a team of TAs. Okay, someone else is getting into the chat. Great. So we have 4 TAs for the course. We have Ibo Yao, Tianxin Tao, Jake Wong, and Mandy Wong. They all took the course before, and Tianxin was also TA already in I think 1 year ago. So these are great guys, and please you will take the labs with them. They will eventually post the Zoom links for the labs. I will give a little bit more information about in this lecture in a couple of minutes. And yeah, so basically this is the staff, right? Remember, we are using Piazza, and if you have any questions, please use Piazza as your first resource. You can also email me. The information of my email is on the webpage. But yeah, I will talk about that later. Okay, great. So now let's talk about computer graphics. Let's literally jump into our stuff. Okay, so what is computer graphics? First, let's talk about a concept that sometimes it's seen, at least like academically, is seen like a wider concept, right? That is imaging. So imaging is any technology to create, preserve, or duplicate images. This means that, for example, even to like keep or store film is considered imaging, right? But we are not in the business of preserving or duplicating, for example, like cinematography film or something like that. Right? We are in the business of creating stuff. Now let's talk about the creation part of imaging. So again, if you go to either Wikipedia or certain old books, you will see that imaging, the creation of images, is kind of, it has several topics involved, right? So one of those is 2D imaging. I will talk about that later. Another topic is computer graphics. That this is usually related with 3D, and is usually when a virtual camera is involved, right? Again, this is a very academic definition. There's also visual arts that it involves digital photography, sculpture, sketching, and later imagery that is like 3D scanning for environments, or medical imaging. So this is a very short list, but it's like we have like a huge list that in theory is involved in the creation imaging stuff, right, or concept. The thing is that more recently, computer graphics is actually known as that wider concept, right? So in fact, computer graphics now is seen as the concept that includes all the technologies that I mentioned earlier. So computer graphics in the end is the study of algorithms and systems for creating images with computers. It means that almost every single image that you can see like synthetically created by a computer is in the end is computer graphics. So yeah, so basically what happened is, before computer graphics was a part of imaging, now imaging is part of computer graphics. So computer graphics is like everything, okay? And this is important because the first thing that you need to understand about computer graphics is what are the topics of computer graphics. The topics, what I mean with topics is areas of research in computer graphics. And again, this is a short list. It's not necessarily complete. You will see why. So we have imaging, we have modeling, that is our area of research. For example, here in my group at UBC, is digital geometry processing. It's called modeling. We also have rendering, animation, interaction, simulation, digital characters, virtual reality, augmented reality, capture, sketching. Oh, sorry. someone is asking something. Will the course be recorded? Yes. I will explain a little like more information about the course, but at the very end of the lecture. But yes, every single session will be recorded. By the way, I need to admit someone else. Yeah, every single session will be recorded, and we will post the links on Piazza and also on the webpage. Okay. The only part that you will not see on the recording is the chat, because that could break the privacy of obviously the participants, right? So I am recording everything in Camtasia. I will create an MP4 file at the end, and that is the file that we will post. I'm not sure if we will publish as a downloadable file, or maybe we'll just post it on YouTube as a private link, and we will give you the link. Yeah, I also didn't see the red dot. This one isn't being recorded right now. Okay, I'm not recording. I am recording locally with Camtasia in my computer. I'm not recording using Zoom. So don't worry. If you're not seeing the red dot, don't worry. Don't freak out. It's being recorded in my computer using Camtasia. Okay, so let's continue. Do you have any other question? Okay, thanks. Yes, I think everybody is okay with this. Perfect. Okay, so let's talk about these topics of computer graphics. So the first one that is on my list is imaging. Okay, and imaging, and you will see in this part of the presentation, this is kind of where we are on the presentation. We are talking about computer graphics. We are talking about raster 2D imaging and raster images, right? So 2D imaging has like two flavors, or two different type of images. So one is raster images, are basically composed of individual pixels. This means that this image, for example, if I zoom in the image like very close, I will see that it's actually composed of individual tiny squares of color, right? So each element on an image has an integer coordinate position, and in the end, a 2D image that is a raster image, we call it, that it is a digital space or a image space. And there's something very important to understand of raster images. The image space or digital space is a non-Euclidean space because it's not continuous, right? I mean, we have only integer positions for each pixel, so it's not continuous. And also for each pixel on an image, it has a finite number of neighbors, right? And it doesn't have a infinite number of neighbors. So that is why it's a non-Euclidean. Again, this is only an introduction. You will see why this is important, but it's also important because I will probably ask you this on a quiz later. Okay, so this is one type of imaging, raster images composed out of individual pixels. So this is, for example, what you can do using Photoshop or GIMP or basically any picture you can take from your computer. Sorry, from your cell phone is basically a raster image, right? It's made out of pixels. The other type of 2D imaging is vector images. So in contrast, vector images are composed of curves. So in this case, the computer, there's an algorithm that tells the computer that certain area of your monitor, right, needs to be filled with whatever color you prefer, right? And that area will be limited by curves. And those curves are typically a certain type of curve that is called Bezier curves. We will see the math of those Bezier curves. And the difference with vector images is that if you zoom in to an image that is vectorized, you will never see the pixels, right? Because every time the computer refreshes the monitor, it's there's an algorithm that is recreating the image based on this curve information, right? So you will never see the pixels. It's pure math that is basically creating the image, right? Another person is getting into the class. Yeah, I'm getting this people asking for admission. So again, please try to be on time. Great. So that was 2D, right? 2D imaging. Now this is another topic, completely different, that is modeling. Modeling, in this case, 3D surfaces. And this is a type of data that also comes like in different flavors or in different types. So the first type is CAD model, or computer-aided design models. So these are typically surfaces or models that are also defined by curves. So this is basically, we were saying that raster images are pixels. This is what you can do, for example, with Photoshop. Vector images are based on curves. That is what you can do, for example, with Illustrator, right? If any of you know what Illustrator is, it's a like graphic design software. So this is basically the equivalent for vector images, but in 3D. These are volumes that are defined by curves, and I will show you an example in a couple of minutes. You can also have surfaces that, instead of being defined by curves, they are defined by faces. These are called polygon meshes. So in this case, for example, this 3D model, all these objects are not defined by curves, but tiny faces that sometimes can be triangles or sometimes can be quads. So it's basically a geometric entity that represents a plane, right? So this type of data is called polygon meshes. And this is the equivalent of raster images, but in 3D, right? So I will show you an example. I will jump right into an example using 3D Studio Max, and I will tell you a little bit about this software. In the last part of our lecture today, I will tell you what are the required software or required programming languages that we will use, but I will also use certain type of supporting software, okay? And 3D Studio Max is one of those. Sometimes I will use Photoshop, or I might use Illustrator, or I might use Blender. This doesn't mean that you need to have 3D Studio Max installed into your computer, okay? So please don't freak out. Although if you want, you can. 3D Studio Max is free for students. So maybe in the next lecture I can show you like the process on how can you download it. But again, it's not required. I will use this type of software to show you examples of something, but none of the assignments or anything is literally related with this. Okay, so it's taking a little bit of time to load 3D Studio Max, my computer. So let's jump right in. So this is the example. This is the example I will show you. So we have two cylinders. One is based on curves, and the other one is based on polygons. And again, because I'm waiting this software to load, it's not loaded yet. Okay, so I will jump into another topic and I will come back later. Okay, so as we said, we can have 3D models or surfaces that are made out of curves. We can have models or surfaces that are made out of faces. We can also represent volume in modeling, and volume can sometimes be represented with voxels. So voxels are the equivalent of 3D of pixels. So if you have an image in 2D and you discretize that space into tiny 2D pieces, those pieces are pixels. If you have a volume, right, and you discretize that volume into tiny cubes, those cubes are called voxels, right? Here's another example. You can see the Stanford bunny. This is a very famous 3D model in computer graphics, and this is an example of a Stanford bunny voxelized using 1 millimeter cubes or 0.6 millimeter cubes or 0.4 millimeter cubes, right? If I discretize the space or divide the space in tinier cubes, I got like more definition from the bunny, right? And There's another way of representing volumes. It's called tetrahedral meshes, and this is a bit different. It's similar to voxels because in the end, you are representing volume, but there's a difference. Can you spot like the very obvious difference between this type of geometry, which is voxels, and this type of geometry, which is tetrahedral meshes? Can anyone say it in the chat? Which renders okay. They're not cubes. Yes, that is one different, of course. So they're not cubes, they're tetrahedrals. Triangle versus squares, yes. They are in the same size, a smooth surface. Yes. So oh, okay. The chat is very fast, obviously, but yeah, someone said smooth surface. Yes. This type of representation, it's is preserving the outer surface, right? And also each element, it doesn't necessarily have the same size. So if you see, in the case of voxels, all voxels have exactly the same size. You define the size when when you're about to start to discretize the space, but once it is discretized, basically your entire mesh is now formed by these cubes, and all cubes are exactly the same. But in this case, it's not, right? You need to preserve the outer surface, and the inner parts, these inner volumes, can have different types of different shapes. Continuous versus non-continuous space. Well, both are non-continuous space. Very good question, Aideen. They're not continuous, right? Because either if you're working with voxels or tetrahedral meshes, those are non-continuous spaces. And also someone was asking, again, the chat is super fast because there are a lot of people here. Someone was asking okay, which renders are the fastest? Curves, polygon, voxels, or tetrahedral meshes? Very, very good questions. Depends on many stuff. It depends of the type of render you're doing, and so the time you take to make a render, it depends on the type of geometry you are rendering, but also it depends of the type of rendering technique that you are using. So for example, for rendering lines or curves, you can render curves using single pixels, or you can express the curves as meshes, creating triangles, and that will take a little bit more time, right? But in general, what can drive the timing of rendering time, it is the number of geometric entities you have. So it's so maybe you have a voxelized geometry, but you have not much voxels, so it will be super fast compared with maybe a mesh that it doesn't contain volume. It is only the outer surface and it's made out of triangles, but you have like 60 million triangles, right? So the one with the 60 million triangles will obviously take a lot longer in rendering. Do typical GPUs work more efficiently with one type over another? Very good question. That is a very technical issue in terms of hardware. In general, hardware, like GPUs, work with triangles, and you will see later that one thing is how are you representing or expressing the geometrical entities mathematically in your computer, and the other thing is how the GPU will actually render that thing. So usually GPUs are in the end working with renders. Working with triangles. So if you have tetrahedral or hexahedral meshes or voxel meshes, you translate those geometries into triangles, and then you send the triangles to the GPU. This is something similar to what happens with the 2D imaging, the vector images versus the raster images. So again, if I am using Illustrator and I want to zoom in into a vector image, right, I will not see the pixels. But that doesn't mean that there are no pixels. They are pixels. So every time my computer is refreshing my monitor, which is usually 60 times per second, 60 hertz, the algorithm needs to redo or recreate the image, and is doing something called rasterizing, that is basically turn that geometry into pixels, right? Which is more similar to raster images in 3D surface wall box. Okay. Splatter. Yeah, I also can't. I also can't understand what you mean. What do you mean by splatter? So you're saying polygon meshes can be splattered onto 2D surface while voxels can't. Projected. Oh, I see. Okay. So by splatter, you're saying that because it's a surface, you could basically like unwrap the surface into a 2D surface. Voxel, of course, you cannot do that because it's a volume. Yes, you're right. Then Paul is asking, if the monitor turns into pixels, why don't we see the pixels for the curves? Very good question. This question will be answered when we will actually see the algorithm for rasterizing. But I think with the demo I will show you right now, you might understand what I mean. So this is trees to the max finally. So let me show you something. I will show you a demo that compares the difference between surfaces composed by curves and surfaces composed by triangles, okay? So this is based on curves, this is based on polygons. So both objects seem very similar. By the way, please say yes if you can see the trees to the max view, please. Yes, perfect, excellent. Okay, so what is the difference? So if I go and take this object here, I will change my view to front view, for example. Okay, and if I select the sub objects of this geometry, you will see that this cylinder here is formed by Bezier curves. Again, maybe for some of you right now, the concept of Bezier curve is new. Of course, it will be new, but don't worry. It's just a type of curve that has a very specific mathematical equations to be formed. But in the end, it's just a curve. So basically, this cylinder is formed by two circles that are connected by straight lines. And if I move the control points of those curves, I can modify this object very easily. Okay, these are control points that determine how the curves are created, and because the surface is an interpolation between those curves, the surface is in the end just reconstructed every time, right? Difference with this object here, this is formed by polygons. So this also looks like a cylinder, very similar, right? If I turn the inner structure of this object, I will see that these are triangles, right? These are a lot of planar faces that are mimicking the surface, right? But the information that is in the end encoded here is position of triangles. So if I want to, for example, distort this object as I did with this one, I would literally need to like manually move groups of vertices, and it will be like super painful job. It will take a lot of time, right? Because those are individual entities. This happens, is the same that happens, for example, with an image, right? If I have a picture that I took with my cell phone and it's something that I want to modify in Photoshop, for example, what I have is just pixels, right? I need to modify each pixel individually. If I have a design created in vectors using Illustrator, I can go and modify whatever I want because everything is just based on curves, right? Okay, great. So, sorry, one last thing. The thing is, similar to what happens with 2D images, vector images versus raster images, when we have geometry that is based on curves, there's an algorithm that is creating that surface, interpolating those curves, but in the end, my GPU needs triangles to actually show this render to us. Okay, so everything in the end needs to be translated to triangles. So if I select this object and I go here, I can see that the surface has something called view steps. This is in 3 to the max. I mean, this name can be different in different areas, but these are the actual steps that the algorithm is using to recreate the shape. So if I decrease that number, you will see that the resolution of the object is kind of getting weird, right? And if I collapse this object into an editable poly, I will see that the object was in fact created by polygons. The only thing is those polygons are recreated every time I am refreshing my computer, and so I, as user, I don't need to deal with those polygons because I have this other structure that is based on curves. Okay, going back to the question by which is more similar to raster images in 3D, voxels or polygon meshes? Very good question. So the most similar to raster images in 3D will be polygon meshes, and in some sense also voxels, right? But the difference is polygon meshes are describing surfaces and voxels will describe volumes. And someone else is asking, would the polygon model render fast then, since the GPU uses triangles? Again, yes and no, because it doesn't matter what type of geometry you have. In the end, that geometry needs to be converted into triangles, and then you send everything to the GPU. Yeah, many of these questions. I loved your question, by the way. You're doing a great job by asking this, but you will understand way more of this when we understand the pipeline, the rendering pipeline. Okay, I will continue because this presentation is huge and we still have a lot of topics to see. Okay, so I was saying that in terms of voxel, in terms of volume, we have voxels, we have tetrahedral meshes, and we also have hexahedral meshes. Right? The difference is that from outside, tetrahedral looks like triangles. From outside, hexahedral meshes looks like quads. Right? That's the only difference. But this has the same concept from tetrahedral meshes. They need to preserve the outer surface, and the entities they don't have exactly the same size, right? Remember, voxels, every single entity, every single cube needs to have exactly the same size. Okay, another topic completely different on computer graphics is procedural modeling. These are techniques to create models or complicated models, complex models, based on a set of rules. This is super important in video games, for example. Imagine you have a company that you're creating video games and you're creating like super large scenes for futuristic cities or whatever. And you have two options. You have one option is to have 200 artists modeling all those buildings, or you have the other option of having maybe a couple of artists with a lot of computer science, a lot of computer scientists, right, that can create like rules or even learning techniques, machine learning techniques that can produce 3D models automatically using rules or using math. Someone is... Oh, sorry, someone missed the hexahedra. The hexahedra looks like quads. Basically, it's a face of 4 sides. Yes, so this is procedural modeling. Here are a couple of examples of procedural modeling. You can create huge environments automatically. So, for example, these environments, there was no artist involved directly in creating those shapes. Right? Those shapes are just created automatically using math, using rules. There are there's a lot of research involved in this. One of my favorite scientists in this area is Peter Wonka. I think this Professor Wonka is on I think it's on Arizona State University. I'm not completely sure. He was one of the first a researcher that began create algorithms for creating like automatic algorithms for creating cities, for example, and it's just amazing. But okay, so next topic is rendering. We will cover a lot of that on this course, and there are two types of rendering in general. One is online rendering or real-time rendering. This is the rendering that happens in real time using your GPU, okay? And it's different from offline rendering or pre-rendering. That is basically, it can happen in your GPU also, but usually happens in your GPU. But these are usually what happens with offline render is this is when you want to create like the most realistic images as possible. You are literally trying to imitate how light works, and you have the absolute best quality possible for rendering. That is usually offline rendering. It takes a lot more time. It's not real time. And usually the technique that is involved in here is called ray tracing. We will do ray tracing. Actually, the last assignment for this course will be a ray tracer. You will actually create an entire ray tracer from scratch, which is super nice. Okay, let's continue. Animation, again, a huge area of research. I will just say that exists because we have actually a course on animation from Michael van de Pen. So please, if you're interested in animation, please go and take that course because animation is super huge. We will see just a tiny amount of topics related with animation in this course, but it will just be super quick. Interaction, this is another area for computer graphics. This is usually human-computer interaction. There are also a lot of courses at UBC regarding human-computer interaction. Simulation, this can be physics simulation like fire, water, any type of fluids. Again, cloth simulation also. This is a huge area. It's obviously very related with physics. And also there's online simulation that happens in real time in your GPU, and also offline simulation that happens like a pre-computation. There's a quick video here. Sorry, it's very. These, for example, these are some examples of simulations done in a software called RealFlow. RealFlow is a software that was like very popular in like early 2000s, and the creators of this software actually they won a technical Oscar award for creating this. Before RealFlow, it was basically impossible to create water for movies, and all the water for movies that you've seen in before the creation of RealFlow, they were just like miniatures, and this basically revolutionized the way of making movies. This is an example of a simulation created in real time. This is a link. You'll able to see the simulation later at home. And digital characters, also another huge topic in these areas. There's also a course on digital characters or human virtual humans. That is a course from Dinesh. Again, if you're interested here, it's super interesting. Obviously, there's a lot of rendering and modeling and a lot of all the stuff that we already mentioned. It is also involved in digital characters, but in general, digital characters is more like the study of the how the skin deform and how the skin looks and many stuff. This is virtual reality, also a huge area. That is the area in which I am involved. So my research is it involves surface reconstruction for VR drawings. I will probably have no time to show you this. Okay, let's do something. We have 7 minutes because we need to finish the course. We need to finish the lecture at exactly 50 minutes. So it's not 1 hour, it's 50 minutes because the department asked me to leave the last 10 minutes for you to take a break. So I will do something. I will show you this on the next. I will show the next slides on the next lecture. So I will jump into the information about the course because that is super important. That is more important. Okay, so for example, what you will learn in this course, that is important. You will learn, we will study the computer graphics algorithms that usually stay forever. Some of the math involving computer graphics has more than 100 years, and we will probably use it for the next 3 because nothing stays forever. So we will actually see new alternative mathematical tools or algorithm tools that sometimes can solve the same problems with easier or faster, right? So we'll see like the usual and more traditional way of solving things and also some new things. We'll talk about 3D shapes, transformations, rendering algorithms, shading models, basic animation algorithms, ray tracing. This is kind of the topics of math that we are going to cover. So we will use vectors, matrices, coordinate systems, transformations, linear affine, forward kinematics, inverse kinematics, quaternions, rotors. Here is in rotors and intersections. Here's where the new stuff will be. So we will have a little bit of geometric algebra, a little bit of projective geometric algebra. Don't worry, you don't need to know anything about that. I will explain everything. We'll see barycentric coordinates, Bezier curves, and whatever, Voronoi diagrams, and a lot of stuff. There's a lot of math involved on this. Required software, we will use JavaScript, GLSL, C++, WebGL, and 3.js. So this is a very practical course. We will have several assignments. Someone is saying, oh God, oh F. Okay. And supporting software, we will use GeoGebra, Trees2Max, Mastrip, but this is not required software. This is supporting software. It's the software that sometimes I will use to explain concepts to you, but that does not mean that you need to have that software, that you need to learn that software. So don't freak out by the supporting software. If you want to install it, if you want to use it, that is perfectly fine. But that is the software I will use to explain stuff. The required is this. We require for you to learn or to know about this. This is what we will not learn or we will not cover on the course. We will not cover like super deep details on hardware. Okay. We will also not cover like OpenGL or DirectX or libraries hacks because they change maybe the next week, so it doesn't make any sense. We will not cover software packages. So for example, if I am using Blender or Trees2Max or Photoshop to explain something, that's fine. But I will not teach you Trees2Max, or we will not teach you how to create images using Photoshop, right? Because we are on the computer science and math approach, right? We will not show artistic skills, right? We will not go also in deep theoretical proofs, so don't worry about that. This is not a theoretical course. We will see a lot of math, but I will not ask you in any theory assignment or a midterm or whatever. I will never ask for a mathematical proof. We will also talk a little bit of machine learning, but we will not go in deep into machine learning. So for example, in terms of rendering, machine learning is creating a huge impact in rendering, specifically in ray tracing, but I will not go in deep. We will mention a couple of stuff, but I will not go in deep. So the prerequisites are these courses here. This is what the department asks you to take this course, but I don't know these courses. I didn't study my undergrad or my master's here, so I obviously don't know these courses. This is what I need. Basically, is linear algebra, basic algorithms, basic data structures. I mean, basic. I mean that you know what is a tree, for example, right? Basic geometry from high school geometry, and also obviously coding and debugging skills, right? Because this is a practical course, and you will need to code and debug, and it's super important. This So the communication, so the lectures are going to be on Tuesday, Wednesday, sorry. Oh, this is wrong. It's Monday, Wednesday, and Friday. Sorry, this is wrong. It's Monday, Wednesday, and Friday, 3 p.m. to 4 p.m. And they will be recorded. The labs will be also on Zoom, and also they will also be recorded. Here's a web page. We have a lot of information there, and we already, and I am changing actually the website almost daily, adding more stuff. Canvas, super important. When is the first lab? Very good question, Ario. I think the first one is on next Tuesday. Tuesday. They start on September 15th. So the labs are always start in the second week. And grading, super important. So we will have 4 theory assignments and 4 coding assignments. Okay, these are the percentages. The first one that is intro, that is already on the webpage, and you have 1 extra late day because we started the instead of starting on Wednesday because of the strike, we started today. So you have 1 extra late date, and you see that for transformations, shading, ray tracing, and theory, you have bonus points. This is super important. Those assignments have a certain thing that you need to fulfill, right? A certain, and those assignments will have something super challenging that if you can get that, you get those bonus points. Those bonus points are going to directly to your final exam. So if someone can perform, or so if someone can do all those assignments, including the bonus points, again, getting the bonus points will be challenging, but it's doable. Sorry, it's my alarm. That means that you can get up to 20 points already for the final exam. And the final exam is only over 100. So it will be super nice to start your final exam with 20 points already. Okay? And we have 3 late days for use during the term. And something that is also super, super important is that we don't count weekend days. So we don't count Saturdays and Sundays as late days. So for example, I usually put the deadline for the assignments on Friday, meaning that if you, instead of delivering your stuff on Friday, you deliver your stuff on Monday, it's only 1 late day. Okay, so you have the weekend also to work. And the expected outcome is obviously have a lot of fun learning. This is a fun course because we will create amazing images, and it will be very nice. And an expected outcome, at least for me, is that the final project that you will deliver, especially the one on ray tracing, we will probably send your work on the SIGGRAPH faculty submitted student work. I will give you a little bit more details because I think we end for now because we have only 15 minutes. Let me see if there are a couple of questions. Are labs just office hours? No. Very good question, Lauren. Labs, in the labs, the TAs will lead you into the technical part of doing the assignments. So for example, for assignment number 1, you need to code in HTML and JavaScript, and you will need to create some shaders in GLSL. They will basically give you like a jump start to that, and they will actually do live coding in the labs. Of course, a certain part of the lab will also be like asking questions, right? So it will be similar to office hours, but in general, labs will be just working and solving questions about the assignments. Very good question, Gabriel. The participation is super important. Thank you so much. And I think this will be the last bit that I will say, because we still have 3 minutes. We have 2% of participation. We cannot take into account participation using the chat with Zoom, because that will be unfair for the people that will see this as a recorded session, right? So the participation will be take into account like this. Almost every day, I mean, ideally, after each lecture, we will post a quiz on Canvas, and you will need to answer that quiz. So basically, the participation is answering the quiz on Canvas. And we might also put some participation points for people on Piazza that are like super helpful for its classmates. So if someone, for example, for some reason couldn't answer some of the quizzes and is worrying that it doesn't have enough points for participation, but that person is like super active on Piazza, and we know that is like answering questions for everybody all the time and like participating a lot, that is also counting. That could also count for participation. Canvas quiz. No, very good question, Ario. No, lecture day. So the quizzes are going to be after each lecture day. And sometimes we will not post quizzes, right? But ideally, yes. Ideally, every lecture day. Okay, someone says every day, including weekends and holidays. No, only lecture days. Yes. So the math review, I will record the math review tomorrow. So I will upload the math review probably on Sunday or on Saturday or Sunday. And if you don't have time to see the math review before Monday, don't worry too much, because the first the following two lectures, we will not use math yet. I mean, not too much. So don't worry too much. So you can see that session maybe on Monday or Tuesday. Yes. Okay, guys, I need to finish here. It's 3:55. Thank you so much. I hope you like this, and I hope you are as excited as me, because I am super excited. Thank you so much. Bye.